So there were actually 60 possible, and I took it out of 54. So everybody got spotted like 10%. And there were some pages that were people struggled on, and so I think some cases where I could not follow the work at all, I gave you 1 point. I was like, okay, we'll do that. So let's take a look at, there were 6 multiple choice questions. The first one was, and it's funny, well, not really funny, but in my chemistry and context today, we're talking about water, and we talked about solubility, and I had one slide about the solubility rules, and they're like, I said, yuck, I hate the solubility rules, and then they're like, I can see why. So I said, I'll pass that along to my Gen Chem 2 students. If you look at the solubility rules, as it turns out, the zinc sulfide and copper 2 hydroxide are generally insoluble. So E was the answer to the first question. The second question was a question about when will Kp and Kc be the same? And that will be the case when the change in number of moles is 0. And so you're looking for, I know these are kind of offset, but for D, actually we have 2 moles of gas going to form 2 moles of gas. So that's where then your equilibrium constant for in partial pressure and in molar concentration will be the same. For number 3, if you have a high, and again, I don't memorize these things, but if your Kc is high, that means you have a lot of products. Because it's always products over reactants. So B is the best answer there. The next page, which of these is always correct? And so actually the first and the second one is always correct. It's always correct that the concentrations, the product will also appear in the numerator of the top. That's always true. Number 2 is also true that reactions will favor the formation of products if your K is large. 3 is not true. The equilibrium constants have units of atmospheres for gas reactions. That's not true. Question number 2, which of these regarding your constants, your equilibrium constants is true? And only 2 is true. Number 2, it's true that the temperature will give you, and I talked about that. It's not true that the equilibrium constants have nothing to do with kinetics. And you cannot have a negative equilibrium constant. So, because it's a ratio of your products over reactants, you just cannot. Question 6 then is, notice I went ahead and added heat on the product side because it was exothermic given that delta H. I don't think we needed that though. But the correct statement is E here, that your Kp, also your Kc, will increase and the reaction will proceed in the forward direction if you cool it down. And here's the deal, I guess I did need to put heat over there. If we cool it down, then we're actually like removing heat, that's like removing product, and that's why it will actually proceed in the forward direction. Another way to say forward direction is form products. It's the same thing. So the next one, maybe this is where I didn't need to have heat. So I have several questions. You only had to tell me what was going to happen to the moles of CH4 when I did this sort of thing, when we shocked the system. So equilibrium constant expression I kind of put up there. Notice that I have little squiggly marks here, and they're down here in the questions. If we monkey with the calcium, the CaO, or if we monkey with the calcium carbonate, then they're going to have no effect because they're solids. So adding more H2O is going to push it to the product. That's going to reduce the CH4. Calcium hydroxide, or excuse me, calcium oxide, again, no effect. Adding more H2 is going to push it back, so we'll get more CH4. Removing some H2O is going to pull it over to the reactant side. We'll get more CH4. The next one, calcium carbonate, again, since it's a solid, has no effect. Doubling the volume of the container will favor the side that has more moles. So that actually is the product side, so your CH4 will decrease. Adding a catalyst will, although it will happen more quickly, will have no effect on the moles. For H, since this is it's endothermic. Adding more heat will actually favor the formation of products, which will decrease your CH4. Adding an inert gas like xenon, I said neon, like xenon will have no effect. Doubling the partial pressure of the H2 is like increasing the molarity or increasing the H2, and so that actually will favor the formation of the reactants, which CH4 is one. Now for this next one, in this one we were given the molar concentration of everything, and we were supposed to, this is the one where you didn't have to solve it all the way. So we're going to end up with an answer that's going to have some X's in it, basically. So first off the bat, we need to come up with the initial molar concentration of everything. We can do that using the moles and the volume, come up with the initial molarity. And actually, to know whether we're going to add our X's or subtract our X's, we need to take a quick look at where it was at with regard to the Kc. We had to come up with a QC. So took these molar concentrations, plug them to reaction quotient, come up to find the reaction quotient is smaller than our equilibrium constant, and since it's smaller, that means it needs to proceed to form products. So only then down here in my ICE table could I go ahead and show that I was going to be increasing my products. So the stoichiometric coefficient in front of everything was 1 instead of but, except for the H2. So I have a 3 coefficient from the H2. So we're going to do plus X for my CO, plus 3X for the H2, and minus X for each of the 2 reactants. So we, at equilibrium, we take the initial, we apply the change for everything, and then these are the quantities that get substituted in for our equilibrium constant expression. So leave it to Beaver, leave it to the X's. So looking for molar solubility, if we let X be equal to the molar solubility of the magnesium hydroxide, again, I would just encourage you to kind of doodle in a way, write the equilibrium between the insoluble salt and it ionizing or breaking apart into cation and anion. This will clearly show you then we have, actually, if we do them, we're going to have 2 hydroxides, okay, on the product side. So that kind of sets that up. Then the KSP expression would be this, where we have molar concentration of magnesium raised to the first power molar concentration of hydroxide ion squared. And this then, the KSP was given the problem 1.8 times 10 to the minus 8. Then if we go ahead and substitute in our X and 2X into our equilibrium constant expression, our KSP expression, and then solve for X. So X is 1.7 times 10 to the minus 4th molar. So for this other one, we actually then, we're going to try to dissolve the same salt in something that already has a common ion. So actually, to work this problem then, we're still dealing with the magnesium hydroxide solid in equilibrium with its dissolved species. So this all still applies, but meanwhile here, your sodium hydroxide has dissolved entirely, that's the one-way arrow, to show that if it's 0.1 molar in NaOH, it's 0.1 molar in Na+, and also 0.1 molar in the hydroxide ion. Then when we set up the ICE table for the equilibrium of the insoluble salt, now we have an initial change in that equilibrium. Initial for magnesium, nothing. Initial for our hydroxide is brought by the sodium hydroxide, 0.1. So now, kind of like what we did the problem in pure water, we have an X and a 2X for the from the stoichiometry of your insoluble salt. So here we have take the initial and apply the change, and at equilibrium we have X magnesium, and at equilibrium we have 0.1 plus 2X. And this was where, and actually in Unit 4, we're going to have one, if not 2, important assumptions. This is what we call a simplifying assumption. So this is where we need to invoke this to get life a little bit easier for us. If we assume the amount that dissolves, which is X, that's the molar solubility, is appreciably smaller, double less than 0.1, which is your common ion, then this quantity right here, 0.1 plus 2X, becomes simply 0.1. Makes life a lot easier now. Now when we go over here to plug in our equilibrium concentrations, we have X for our magnesium, we have 0.1 for our hydroxide. Don't forget that our hydroxide, we had to square it. Okay, so that's the square here, that we're after the same KSP. So here now, when we solve for our molar solubility X, we get 1.8 times 10 minus 9th. And again, you would expect it to be less soluble when you have the common ion there, which it is compared to up above in the pure water. On to the next one. This one was kind of, I was trying to think of when we did this. We might have covered this one kind of recently. So you can kind of just see by the picture that we're dripping in silver nitrate. Of course, our silver nitrate is going to break apart and give you silver and nitrate to spectator ion. In question is that silver cation, is it going to go ahead and precipitate with our chromate, or is it going to precipitate with our bromide ion? So kind of like, and I think I did this on, this is Friday, I think I did this on Wednesday. Kind of like you see what I did on Wednesday, I kind of bring down our possibilities here. Of course, this is, the formula is important, bless you. And actually, I gave you the formula up there. So you're talking Ag2CrO4 solid in equilibrium with its dissolved species, 2Ag plus CrO4 2 minus. Write the KSP expression for that. The KSP was given for the salt. Do a similar thing on the bromide side. And then on both sides, actually, we're coming up, I called it threshold. We're coming up on the silver. How much silver do we need to drip in order to have the chromate that was given precipitate? So we can take the KSP expression, rearrange it for the silver ion, and get the threshold for the silver chromate is 1.0 times 10 minus 5th. For the silver bromide, it's 2.5 times 10 to the minus 10, 11. So of course, since this is smaller, it's going to happen more quickly. So your silver bromide will precipitate first. And then a follow-up question was that when your silver chromate does start to precipitate, what will be the molar concentration of your bromide ion? So this was one where we go ahead and we kind of have to look at the, let's see. Yeah, look at the threshold for what the silver ion must be in order to get our silver chromate, and then go back to this KSP expression, rearrange it for bromide ion, now substituting in the threshold from your silver chromate. So there's that. This one, and I maybe should stop calling it Hess's Law because it is kind of different than Hess's Law. But it reminded me of Hess's Law. Hess's Law is more like with the delta H's and all that. But this is where we were given these three equations. I labeled them 1, 2, and 3. And this is our equation of interest right here. So it feels similar to Hess's Law in that you're going to kind of look at each of those, 1, 2, and 3, and see what you need to do to them in order to combine them to get this reaction of interest. So you can see what I did for the first one was to take it times 1/2. I did for the second one was to reverse it, thus the negative, and also take it times 1/2. For the third one, I also reversed it and took it times 1/2. And you kind of see me manipulating in here. And then when I do that, notice that things cancel out, and some things, not everything, thank goodness, cancels out. And I actually do get my equation of interest. So if that's the case, then these new KPs, then, if I multiply them all together, I will get the KP of interest. So in this case, though, you had to remember that if we've manipulated an equation, we also have to manipulate its KP by raising it to the power. And in the case of reversing them, actually, it's raised to the -1, just because we reversed it. In this case, we also took it times 1/2, so it's going to also take it times, so it's -1/2 power. So these are the new KPs. Multiply them all together and get the KP of interest. All right. This one was, what was this one? The biggest thing, and actually a couple of you did the same mistake as I was working this semester, for an answer key, I made the same mistake. So I only took 1 point off. I think it's 1 point. If you can hurry, which I did, and where it says 0.236, it's not moles per liter, 0.236 moles of one of the products. Anyway, it says that you're going to start out with 4 moles of NH3. That's it. 4 moles of reactant, nothing else, in a container that has a volume of 1.50 liters. Good thing about that is if only you have the reactants, you know it's going to form products. So over here on our ice table, we've got minus 2x. The reason it's 2 is because the stoichiometric coefficient is 2. Going to form plus x and plus 3x. Again, in front of the H2, we have a coefficient of 3. So that's our ice table. Now the initial, if we take the moles, 4 moles, and you divide it by 1.50 liters, you get a molarity 2.66. That's where that came from. Of course, initial molar concentration of these guys is nothing. Now, where the N2 comes in is that's the one equilibrium concentration. So I think I have a little mark down here. Actually, we are given this. This is the one that we are given. Again, if you put the moles there, you're in good company. But really, to get molarity, we have to go ahead and divide the moles by the volume. So 0.157, that was at equilibrium, the N2 form. That's also our value for x. Okay, so now in order to get 3x, we're going to take 3 times that quantity. So take the initial, apply the change. So at equilibrium, here's our H2, 0.471. Similarly over here, we're going to take 2 times 0.157. So that's going to be your negative 2x, and that's what we're going to subtract from 2.66 to get the equilibrium concentration of your NH3. Once you have these 3 equilibrium concentrations, you're ready to plug into your equilibrium constant expression and knock out a value for Kc. I think this is the last one. Okay. So this is the one I think I was kind of warning you about. I wanted you to kind of give me the whole enchilada, 1 point apiece up here, to tell me if you take 2 liquids, okay, combine them together, what sort of exchange reaction might happen there. And I actually go ahead and tell you that your lead-2 sulfate is going to precipitate. So one solution had sodium sulfate, one solution had lead-2 chloride. We have the cation and the anion switch partners, so you end up with your lead-2 sulfate and your sodium chloride after the exchange of actions. You know what I'm saying? Exchange reaction happens. And I asked for balanced, so of course to balance it for your NaCl's, you're going to put a coefficient of 2 in front of that. The next thing is I wanted the balanced equation for the equilibrium of the insoluble salt, the thing of interest. So running with the lead-2 sulfate, showing how it goes from its solid, breaks apart in water, looks like this. And then down here, down here, I wanted you to let me know, would you get sludge at the bottom? Would you get a solid sludge of PbSO4 down here? Well, you had to make sure that you could take, you had to come up with the molar concentrations of your lead-2 from your lead-2 chloride, and I kind of showed that down here. It's weird to have just such a small volume, 0.4 milliliters. I came up with the moles of lead-2, 1 times 10 to the 4th, and divided those moles by the total volume. Up here, you can kind of see where I calculated total volume. We had 100 milliliters of one and 0.4 milliliters of the other. And remember, since we're adding, we have to round according to decimals. You have 0 decimals and 2 decimals, so I get 0 decimals. So bottom line, and this happens a lot, if you're adding with something with a dropper, your volume is unaffected by what you're adding with the dropper. So anyway, the molar concentration of the lead-2 looks like this. I needed the molar concentration of the sulfate ion. It's calculated over here. Use the volume, the molarity, get the moles divided by the volume. I didn't need to do all that, did I? Oh my gosh. Anyway, I got 0.50. I could have just taken it from there. I got 0.50 molar sulfate. And then what we're going to do is take these two and plug them into our QSP up above. and to see if our QSP is greater than our KSP. Which, up above then, you can see where you're looking at 5 times 10 to the minus 4th compared to 1.6 times 10 to the minus 8. So yeah, it exceeds, your QSP is larger than KSP, so a precipitate will form. Smiley face. So that's that. I was thinking, and I don't know, you never know whether how to encourage learning, or how to encourage people to, you know, do their best. And I'm not saying people aren't doing their best. I guess I would say you guys have 1 unit left, and it could go either way. You know, it could be like this, it could be like this, it could be like this. I don't know. And in this class, I guess I'd point out a few things. In case you have the fire and you want it to go like this, the way this class is set up is it's small and you have access to me, and so you take me up on it. You do have access to the recordings, and you know, and I know some of you go out there and there's, you know, Khan Academy, there's all sorts of resources. And so it might seem kind of late to put a come on, you can do this, but this is like come on, you can do this sort of thing. The best thing is to keep up with the material as you go along. Like if something's like a little foggy, now's the time to get it, not like right before the test. That's probably not going to clear it because you're going to have foggy right before the test too.
So does Unit 5 lead into the final exam then? Is that why
it's kind of like Chem 1. Unit 5 will actually, we won't have a Unit 5 exam, yes, and it will lead into the final. So you will have some questions related to Unit 5 on your final. Yeah. I just kind of wanted to be encouraging. So, yeah. Let me know if there's a thing I can do, but all right. So let's see how far we get in this stuff. Okay. I get to this point, and actually I teach the subject in some of my other like intro science classes, and when I teach it there, I'm like, oh, acids are H pluses, bases are OH minuses, and you kind of leave it at that. But there's more to it, and the other thing I was going to say with my pep talk is, in all of your classes, including this one, remember it's not just the grade, it's actually the knowledge. So for some of you who are going to go on and use this in your classes, and I think you guys already know that, so I don't need to be saying I'm saying something that you don't already know. But it's not just the knowledge. You will be using this stuff later. But what I started saying is you guys need to know more than the acids are the H pluses and the bases are the OH minuses. But it is kind of like that. So let's start there. Acids, there are the H pluses and bases. And I feel like those are the OH minuses. If we add these together, guess what you get? H2O. It's a beautiful thing. And so that's not a coincidence. Okay? But there's more to it. There's something to be said for that. We're going to build on that. So there's, and this is like four definitions of an acid and a base. So the Arrhenius definition goes like this. And we won't need to use all four. I'll tell you, we're going to go with the Bronsted version. But, and they're all kind of similar, I think. We generally could say something is an acid if it produces H pluses. Where did you just hear that from? Something is a base if it produces OH minuses. So this is the Arrhenius from like the Arrhenius equation. So this is the Arrhenius definition. And that'll get you down the road, but it won't entirely get you down. This is the one that we're going to be using more. So if you put a star next to it, this is kind of what we run with. The Bronsted or Bronsted-Lowry definition looks like this. It's similar. An acid is anything that can produce an H plus. And actually, this is kind of fun. if we look at the periodic table, the element hydrogen, it's atomic number 1. So if this is the nucleus of a hydrogen atom, you're going to say it has 1 proton. I'll just go ahead and do 1 proton. If it's neutral, it has 1 electron, right? The most common form of hydrogen has a mass number of 1. So here's the deal. Mass number, that's equal to the number of protons plus the number of neutrons. So if it has a mass number of 1, how many neutrons does it have? None. So the most common form of a hydrogen atom has no neutrons in its nucleus. That's kind of fun. So if it has gone from an H to an H+, check this out. The electron has gone away, right? So if somebody says I have an H+ ion, you simply have a naked proton. How cool is that? I mention all that because sometimes when people talking about acids and bases get rambling, they will interchangeably use the word proton for an H+. So that's the whole story. Kind of a fun story. So H+ is a proton. Why don't they just say hydrogen ion? Okay. So in this definition, we're going to be dealing more with a Bronsted base is something that will accept a proton, or will accept, remember proton, same thing, H+, accept a proton. But if you're like me, I mean, how cool is this? Doesn't this base accept a proton in OH-? So they're not totally different. You know what I'm saying? Not totally different. Anything that produces hydroxide will accept a proton. By the way, OH- is hydroxide. So there's, I don't know. All right. The third one, I guess there's only 3 we need to do. The third one is the Lewis definition of an acid and a base. And in order to describe what this definition is, I need to kind of talk a little bit about what is a coordinated covalent bond. And I'll show you that here in a minute. But an acid is something that will accept an electron pair, from another substance, and it will form a coordinate covalent bond. Covalent bond, electrons are shared. Okay? A coordinate covalent bond basically is both of those electrons that are shared came from one atom. That's it. And then a base, if they accept it, guess what? The base is the one that donates it. The acid accepts the dot dot, the base provides the dot dot. Okay, so a base is something that provides an electron pair to ultimately form a coordinated covalent bond with another substance. So, NH3, a neutral NH3 molecule, HCl, hydrochloric acid. Let's kind of see how this Lewis definition, and maybe all definitions, I can't remember how that works. Okay, so the little arrows are showing you where the dot dots are going. So here on the product side in a minute, you're going to see these dot dots are going to form these lone pair electrons coming from the central nitrogen atom are going to be the 2 electrons that form a bond with that other hydrogen. And then this actually electrons associated, or 1 electron associated here is going to go with the chlorine. So it looks like this. And so this one, I know these all look the same, and they are the same, but this was the new bond formed with the hydrogen that came from the HCl. And this is an example of a coordinate covalent bond where both electrons came from the nitrogen. So in the definitions we talked about, the proton acceptor, now this is where it gets a little tricky because you have to look on either side of the reaction arrow, in this case equilibrium arrow. The one that accepted the proton was your NH3. How do we know that? Because on the product side, now it's NH4, or NH4 plus. Proton acceptor, okay? And it's also that makes it a Bronsted base, because it accepts a proton. And it's also a Lewis base, because it provided the pair of lone pair electrons to make that new coordinate covalent bond. Looking from left to right here, the HCl is providing the proton, so it's the Bronsted acid. It's also the Lewis acid, which this should always be the case. They should be common acid, common base in all three definitions. It's also the Lewis acid because it was an electron pair acceptor. That electron pair right there went with the chlorine. Okay, coordinate covalent bond. This is exactly what I told you. What is a coordinate covalent bond? If it's important in the definition of a Lewis acid and base. Coordinate covalent bond, like we saw just a minute ago, was when one atom, in the case before it was the nitrogen atom, provides both electrons that are used in the formation of, in the case of NH3 going to form NH4 plus, was formed between the nitrogen atom and that hydrogen coming on. But like this says in italics, once it's formed, it's just like any other covalent bond. You know what double arrows mean? It means it goes from left to right, and it also goes from right back to left again. So we could go backwards, okay? And in that case now, the proton donor is going to be your NH3, so that actually is going to be your acid, and the proton acceptor is going to be your Cl, so that's going to be your base. Okay, I will be talking more about that. So like I said, we're going to go with the Bronsted-Lowry definition of, what did we say? So an acid is a proton donor. When we say proton, it's an H plus. A base is a proton acceptor. I don't know why would it say hydrogen ion, 5 syllables. Proton donor 4. I don't know. Well, with proton donor, we also get the direction it's going to. It's just faster. Proton, hydrogen ion. Okay. Anyway, they mean the same thing. So, in acid-base chemistry, in this subject, we're going to see some B's. And B's here do not mean boron. Okay? B's just here means something. That could be R's. Okay, just something. So we have hydrogen connected to something else, okay, reacting with water. And if you kind of pick it apart, what's going on, you see the water picks up an H plus on the product side. And your B, which is just something, is left now with a -1 charge. All in equilibrium. This is actually kind of a generic way to show a weak acid, a weak acid breaking down. So in this scenario, the proton donor is your HB, okay, that's your acid. Does this make sense if you compare from left to right, your H2O versus your H3O plus? Again, to me, in order to know if it's a donor or acceptor, you have to see what it did on the other side. You see it's accepting the proton, so that makes it the base, proton acceptor. Well, oftentimes what you just saw a minute ago is written like this instead. What's missing is the H2O molecule to pick up the H plus. And I read recently, maybe it was in my notes getting ready for today, or it was in a different textbook, talking about the same subject. Your H plus is very reactive, so probably you're not going to have an H plus running around in there, the proton. It's probably going to catch a ride with a neutral water molecule and makes your H3O plus. Okay. So kind of what we've seen, we can think of your your free proton, your free hydrogen ion, catching a ride with a water molecule to form H3O plus. So this is a hydrogen, we have some words, some nomenclature, some, I don't know what you call it, just some verbiage. So the proton, hydrogen ion, whatever you want to call it, this actually has an important name too. And I know OpenStax, or some of my other textbooks too, use that a lot. Hydronium cation. You need to, somewhere in your vernacular, maybe that's vernacular, know that anytime somebody's talking about the hydronium cation, you're talking about H3O plus. What is H3O plus? Well, I can see the H2O, and it's basically, no pun intended, just add an H plus onto it. So hydronium ion. Sometimes I'll call it hydronium cation, which. So here's the reality of it. Somewhere, and I guess I'll just go ahead and write it right here. Okay, so H plus is the same thing as proton, and now somewhere in there, you have to know that H3O plus, actually, these can be used interchangeably. They can. You're like, they look different. Like, oh, they kind of are, but they're used interchangeably. This is hydronium. In fact, like I was, this weekend, hopefully I'll work some more problems. We are definitely not going to get to the end of part 1, so these won't be due. We'll finish this part up on Monday. But what I start to say is I kind of go back and forth between H pluses and H3O plus too. So anyway, they're the same thing. But you figure there's got to be some differences when you're going to use them in problems, and there are. So anytime somebody talks about ionization, it sounds like a big, scary word, but all they're talking about is dissolving or breaking apart. So when we dissolve like sodium chloride in water, we are ionizing sodium chloride. So the extent to which something dissolves or ionizes will say how strong the acid is. And I kind of think of it this way, kind of from left to right. You start out with your together sort of stuff like HCl or H2SO4 or acetic acid, and then you go over to your product side and say, well, how much H plus do I have? What's the extent of ionization? So a strong acid would mean that you have a one-way arrow, basically, so it all splits apart, okay? And you're going to want to know these. Are there 7? Yeah. I don't have you memorize much. There's 6. This will help you work problems. This will help you in life. Who knows? But this would be a one-way arrow, one-way ticket, one-way arrow to show that on the product side, basically, like if you had 1 molar HCl, you'd have 1 molar H plus. That's how that works. Okay. Now, 1 molar H2SO4, and we'll be talking more about this. Actually, on the product side, you're going to have not both of these. My point's going to be not both of these hydrogens kick off. But you can see the hydrogens kicking off here. 100% ionization. One-way arrow. And here is, these hopefully are the same 6 I have. This is an OpenStax figure. One definition, actually the Ray's definition of a base is one that provides hydroxides, okay? So these are actually some strong bases. I think the Ray's definition is too narrow. I think the Brownstein-Lowry definition, where it accepts a proton, is going to be better. These are strong bases. So like I said, here we have a, I'll underline the word strong. Those other ones were weak. This one's strong. I don't think I said weak, but it's on my slide. So these are strong acids, one-way arrow. Now, again, we're showing that in reality, to me, if you show the hydronium cation on the product side, that's instead of just the bare H plus, the bare proton, that's probably more reality what's happening. catches a ride with a neutral water molecule minding its own business. And remember, the B or the B minus over there is just the thing that was, it's generic. It's a placeholder. So the first one, if I write this as 1 and this 2, you know, these are both ways to show the ionization of a strong acid. But 1 is more reality what it does. And then 2 is just kind of easier work calculation sometimes. But it ionizes completely. So like this says, ionizes completely. You don't have to worry about any of the HBs staying around once it's done its thing. Especially if it's relatively dilute. Okay. Weak acids now, you're going to need a two-way arrow. Weak acids, well, you're going to have some what we call unionized thing left. You're going to have some HB left in addition to your H plus and your B minus. So I have a couple of different ways to kind of show the ionization, the dissolving of a weak acid. One of them is to show your weak acid and to show water molecule, giving your H plus a ride. On the product side, we show the hydronium cation and your B minus. One of the things we know about chemical equilibrium, this is where already hopefully you can see how unit 3 and unit 4 are kind of connecting up. We said you can write an equilibrium constant expression. It's exactly what we're going to do with this. How's it going to go? It's going to be the molar concentration of the product raised to their stoichiometric coefficients divided by the molar concentrations of the reactants raised to their stoichiometric coefficients. If it's in water and water is in this liquid state, it does not show up in your equilibrium constant expression. Okay. So here is writing your equilibrium where your H plus is not shown catching a ride within H2O. This is showing you kind of stepwise what that would look like. It's got a neat name to it, neat fancy name. A lot of things in chemistry or science, once you pick the name apart, you're like, oh yeah, I got that. Protonation of water. Well, I just told you an H plus is a proton. Protonation of water. H2O. We know water is H2O. So H2O plus H is this. So what's going to happen is this H is going to end up over there. You're going to have a B minus on the product side. And when we talk about the Lewis definition of an acid base, this is consistent with that. This too. This is going to be your proton donor. This is going to be proton acceptor. Seems reasonable. This is where I thought we were a minute ago. I wish I was more dramatic about this, but so this is where I whine about we have a KC, we have a KP, we have a KSP. Okay, now we have a KA. KA is just describing the equilibrium of a weak acid. KA. So doing it this way, where we have the water molecule and the hydronium ion, it would look like this. Doing it without catching a ride from the water molecule, it would look like this. The difference is we have an H plus there instead of hydronium ion, which I said you can use them interchangeably. So this is all to represent the same weak acid ionizing only to a certain extent. So it's not a small thing to keep in mind that our strong acids, one-way arrow. Our weak acids at equilibrium, and we use this term, and I think I used it. This guy right here, this is the non-ionized. This is the non-ionized. WA stands for weak acid. So if somebody says like, well, how much What was the amount of non-ionized weak acid? That's what you're talking about. All right. So one of the things, and this actually was a test question,